I want to take a look at limit problems graphically, what this really means. So this is the actual problem that we're dealing with here is that the limit as x approaches 2 of 3x plus 8 equals 14. It'd be an easy thing to do with direct substitution. It's pretty easy, straightforward limit. If x is equal to 2, you're going to get 6 plus 8, which is 14. So if x is close to 2, you would, of course, get values close to 14 because there's nothing weird going on with this function, right? So this is a limit. But what does that really technically mean? The definition of this really is that no matter, well, this is the graph for the function. The blue thing is the function itself. What I'm really saying is that no matter how small a target I choose here, and I'm using capital E for the width of the target there, the epsilon is the traditional symbol for that. I'm saying that no matter how small I make that target around 14, I can get all of the values of the function around 2 to fit within that. So it's getting a little hard to see what's going on. Let's take a closer look here at what we got. If I have a small enough epsilon, this isn't good enough, right? Some of the values around 2 are coming out outside of that target band. I want to get a width down here that's small enough to guarantee that everything in here fits within that target band. And so I'd have to have a smaller delta here, a narrower band, so that it'll definitely fit within that. So for this one, I got to go down from 0.1 to even smaller, something like that would be enough. See, that's good because within this red band, all the values of the function stay within our purple target area there. Yeah, even up in here where we're within that epsilon now. So what we'd like to do is be able to say, no matter what, how small you make this target band, I can find a delta based on that that's good enough to stay within that range right there. We're going to mess around with some inequalities to do that. But now if I shrink this down further, that 0.04 isn't good enough anymore. I would need a smaller delta to go with that epsilon. For bigger ones, this is okay. I'm going to basically have to make this depend on epsilon. Make a little formula right here so delta depends on epsilon so that this band of function values always fits within the target band. I'm just going to jump to what this one is right now, and we're going to see how with inequalities we can figure those things out for simple enough functions anyway. But if I make delta equal to epsilon over 3, because of the slope on this one, that makes it a perfect fit here. No matter how small I make epsilon now, the values within the red neighborhood around 2 are always going to fit within that target band within epsilon of what we say the limit is, which is 14 in this one. So I'm going to go through how the inequalities work to make this happen, to find that little function right there, and then we'll do a more complicated example. We'll look at a picture and find the formula right here. Basically, the key to proving these limits work is being able to find a formula for delta that makes this happen, that keeps our function values within that epsilon band. That's what we're trying to accomplish.